Hi dear students, now we discuss the second theorem, that is Norton's theorem. This is a second network theorem. According to the Norton's theorem, a linear active network, that is explained what is the meaning of the linear active network in the last class. A linear active network with two output terminals A and B. One load resistance is connected here. According to Norton's theorem, this can be replaced or this can be equivalent to a circuit that is consisting of a single current source called Norton current IN connected in parallel with a resistance that is called Norton resistance, and at the output terminals we have the same load resistance RL. Okay, that is, any linear network having two output terminals can be replaced by a network consisting a single current source IN in parallel with a resistance RN. Let me write the statement here. Okay, that is, any linear network having two output terminals can be replaced by a network consisting of a single current source IN in parallel with a resistance RN. Here I will explain what is a concept of IN and what is the meaning of this RN. Okay, IN means there is a current through there is, if you look at this picture here, we remove a load resistance RL, then this terminal A and B will be short circuited. Then the current flowing through this short circuited output terminals, that is the Norton current IN. Okay, that is, let me write here, this is the current flowing through the short circuited output terminals after the load resistance has been removed. Okay, this is the current flowing through the output terminals after the load resistance has been removed and the terminals A and B is short circuited. This is a short circuited current actually. That is, one can say this is a short circuited current, ISC, short circuited current. Fine. Now what is the meaning of the RN? RN is the total resistance measured at the output terminals after replacing the old voltage sources by their internal resistance. If you come back to this picture, the statement will be clear. That is, remove this load resistance and replace all the voltage sources by their internal resistance in the linear active network. Then whatever the net resistance is viewed or calculated between the terminals A and B, that resistance is the output terminal. Okay, that is, let me write here, this is RN is nothing but the resistance measured at the output terminals after replacing the old voltage sources by their internal resistance. Okay, now what will be the current that is flowing through this load resistance RL? That current flowing through the load resistance is denoted by IL. Then according to the Norton's theorem, this IL can be written as IN, that is the Norton current, into Norton resistance divided by Norton resistance plus load resistance. This is the expression for the current that is flowing through the load resistance RL. Okay, that is, I will write here IL is equal to IN Rn divided by Rn plus RL. Fine. Now let us do a problem that will give you a clear idea, that is how to use the Norton's theorem to find out the load current in a given network. Fine. First question, that is, okay, find current through the resistance RL, that is road resistance 5 ohm in the following network using Norton's theorem. Okay, that is, we have to find out the current flowing through this load resistance RL, that is, we will call that the current is IL. Then according to the equation given by the Norton, IL is equal to IN Rn divided by Rn plus RL. Fine. That is, here first we have to find out the IN, then we have to find out Rn. Okay. Now first our aim is find IN. Okay, that is a Norton current we have to first find out. For this, first what we have to do is, the first step, remove RL. We have to remove the load resistance from the given circuit. That is, then this picture that we can redraw like this one. Here we have the voltage source 100 volt. This is 5 ohm. This is 10 ohm. Here you have another 10 ohm. Then we have removed the load resistance from the output terminal. Okay. Fine. The next step, that is short circuit this terminal A and B. Okay. That is, remove R and L, then short circuit the terminals A and B. Fine. Next, we have to calculate what is the current flowing through the short circuited arm, that is through this one. For this, first we have to consider the different loops. Let me first start from here. From the positive terminal of the battery, current starts to flow like this direction. This current is denoted by I. After reaching this junction, it has two paths. One is this one, another one is this one. Then the current flowing through this arm is represented by I1. Then the remaining current, that will be I minus I1, flows through the 10 ohm resistor and finally reaches the terminal between the terminal A and B, and the current flowing through the arm AB is denoted by the same current I minus I1. That is a Norton current actually. We will write this is a IN. Okay. Now this current reaches here, the same current I minus I1 goes, and this will complete here. Fine. This I1 joins with this I minus I1, and then a net current, that is total I, will flow again to this battery. Now we have two loops. The first loop is this one. I consider the path is along the clockwise direction. This is the loop 1. The another loop is this one. This is called loop 2. From here, loop 1, we can write the equation of voltage, that is while going from this direction, that is we will meet the negative terminal of the battery first, that is this one, this portion. Therefore we can write this is a minus 100 volt. Okay, simply I write minus 100. Then while reaching here, that is along the clockwise direction, both the current and the path are along the same direction through the 5 ohm resistor. Therefore, the voltage drop across the 5 ohm resistor is positive I into 5. Then, while coming to the current I1, that is through the 10 ohm resistor, current I1 and the path both are along the same direction. Therefore, this again 10 into I1 is a positive. Then we reached here. Then this path, there is no other resistance. Therefore, the right hand side is equal to 0. Here, if you divide by 5, then we will get this is minus 20 plus I plus 2I1, that is equal to 0. Okay, that is, if you rearrange the term again, then we will get that is I plus 2I1, that is equal to 20. Or this is equation number 1. Now you look at the loop 2. Okay, that is, if you look at the loop 2, the current I and I1 and the path are along the same direction. There is a voltage drop across the 10 ohm resistance, that will be equal to 10 into I minus I1. Then after reaching this terminal A and B, the current and the path, the current through this arm is I minus I1. That and path are along the same direction, but there is no voltage drop. But you come again, you come around this direction, and this loop will be completed if you go in this way. Here the path is going in the upward direction, but the current flow is in the opposite direction. That is, the path is along this direction, but the current is around the downward direction. Therefore, here I can write minus the resistance is 10, current is I1. 10 into I1 is equal to 0. Fine. Now open the bracket. 10I minus 10I1 minus 10I1 is equal to 0. The 10 is common. I minus 2I1 is equal to 0. That is, from this one can write I1 is equal to I by 2. Let me put this is equation number 2. Actually, to solve the equation number 1, we should know what is the value of I1. That is clear from this expression 2. Put 2 in 1, that is I plus 2 into I by 2 is equal to 20. This 2 and 2 got cancelled. Therefore, this 2I, from this 2I is equal to 20. I is equal to 10 ampere. Okay. But to calculate the Norton current, that is, if you look at this expression, that is IN, that was equal to I minus I1. Now we know the value of I1 and I, that is, here we got for the value of I is equal to 10 ampere. Then I1 you can calculate from the expression 2, that is I1 one can easily calculate because the value of I is 10, that is from equation 2, that is this equation, substitute the value of I here, then you will get I1. Okay, I1 is equal to 10 divided by 2, that is equal to 5 ampere. Therefore, the Norton current IN is equal to, there was I minus I1, I minus I1, I is equal to 10, I1 is equal to 5, this is 5 ampere. That is, our Norton current is 5 ampere. Okay, this is the one, we got one required factor, that was, we got the value of IN. Next, if you look to this expression again, now we need to know the value of Rn, that is the Norton resistance. That is our next task. That is the second, to find Rn. Okay, for this, what we have to do is, we have to replace all the voltage sources by their internal resistance. Okay, that is, we have to replace all the voltage source by their internal resistance. And one more thing we have to do, we have to short circuit the output terminals also. That means we have this circuit here, that is this circuit. What we have to do is, we have to replace this voltage source by their internal resistance. Actually, no internal resistance is given. Therefore, I can redraw this picture here to find out the Rn, that is the voltage source. There is no internal resistance. Therefore, the voltage source is short circuited. Then we have here 5 ohm. Then here we have this 10 ohm, and here once again the 10 ohm, and the output terminal, that is, we have to remove this load and we have a short circuit like this. Therefore, we can draw the picture like this. Okay, here you have the terminal A and B. This is the picture corresponding to the statement that we have written here. I will redraw that picture here. That is, short circuited our voltage because there is no internal resistance. Next, we have 5 ohm resistance, then 10 ohm resistance. In this arm, once again a 10 ohm resistance, short circuited, removed the load resistance and short circuited the terminal A and B. Fine, here it is very clear that this 5 ohm and this 10 ohm are in parallel. That is, 5 ohm is parallel to the 10 ohm. As I mentioned in the last class, there is a shortcut to find out the effective resistance. The highest value of the resistance from the combination divided by the highest value divided by smallest plus 1. Okay, 10 divided by 2 plus 1 is 10 by 3 ohm. That is the net resistance between this 5 ohm and this 10 ohm. Now, I can redraw this picture like this resistance and this resistance became a single one, that is 10 divided by 3 ohm, 10 by 3 resistance, and here you have this 10 ohm resistance, and the terminals A and B is here. This is A and this is B. Fine. Now this 10 ohm resistance is in series with the 10 by 3 ohm resistance. Therefore, whatever the resistance is coming between this terminal A and B, that resistance is our Norton resistance. That is effective resistance between the terminals A and B after removing the all voltage sources by their internal resistance and also by short circuiting the terminal and B. Here this Rn we can write, that is the 10 ohm, that is in series with the 10 by 3 ohm. Therefore the effective resistance Rn is equal to 10 plus 10 by 3, that is 40 by 3 ohm. Okay. Now we got the value of Rn and In. Okay, In we have here, that is a 5 ohm, and the Rn we have 40 by 3. Now what do we have to do? The third step. In the third step we connect In, the single current source, parallel to the single resistance, that is Norton resistance Rn. That is the third step. We have the single current source, then we have to connect in parallel. Okay, that is, this is our Norton current source, that is a 5 ampere. Then this is a Norton resistance, just now we calculated 40 by 3 ohm. Then you connect back your RL to the terminal A and B. Then connect RL back to the terminal, connect RL back to the output terminal from where it had been removed. Okay, the same position, the same place we had to connect back our RL. That is, our RL was 5 ohm. Now everything we did, now just to substitute into this expression, that is In into Rn divided by Rn plus RL, that is 5 ampere, Rn is 40 by 3, divided by Rn is 40 by 3, RL is 5, that is, this is 200 by 3 divided by 50, this will be around 55 by 3, and the 3 and 3 got cancelled. This is 200 divided by 55, that is comes around 40 divided by 11, 40 divided by 11 ampere. That is the load current, that is nothing but 40 divided by 11 ampere. In this way one can calculate the load current using the Norton's theorem. If we compare the procedure what we did in the case of Thevenin's theorem and Norton's theorem, in the case of Thevenin's theorem, what we did is we have replaced the whole circuit by a single voltage source that is connected in series with a single resistance source. Okay, this was the case in the Thevenin's theorem. This was our load resistance, point A and B. In the case of Norton's theorem, a single current source that was connected in parallel with a Norton resistance. This was the Norton current, and this was our load resistance RL. Only this is the difference. The difference is here V Thevenin is series with R Thevenin. Here the current source In in parallel with Rn. Fine. Okay. Then the expression for the current we used was IL is equal to total voltage divided by R Thevenin, total resistance, plus R load. Here the total current through the load resistance, that is IL, was, that is the current, Norton current, into the effective resistance. That effective resistance is nothing but Rn divided by Rn plus R. Okay, this is a Norton current. This is the effective resistance. Here I will give you an homework. That it's the same problem that we did in the case of the Thevenin's theorem. The same problem you have to do here also. That is, you have to calculate the value of the load resistance using the Norton's theorem also. We will use the same circuit. Okay. Question is this one. That is, using Norton's theorem, find current through the load resistance 15 ohm in the following network. That is, you have to calculate the current through this 50 ohm resistor. Okay, this is your load resistance RL. If you go back to the previous class note where we did the same problem and we obtained the value of the load current is equal to 1 ampere. And using the Norton's theorem, you do the same problem and check whether you are getting the value of the current 1 ampere or not. Okay. Thank you very much for watching this lecture.